Hello, welcome to this lecture series on quantum chemistry. In this lecture, let me continue the particle and a ring problem. Here I like to give application of particle on a ring problem. What is the application? The application is this. Listen, you can find the lambda max for cyclic conjugated planar systems. Okay, we can find the lambda max value by calculating the energy difference between HOMO and LUMO level, and by taking UV spectra, UV visible spectra. You can also calculate alternatively the rotational constant of the molecule. So you can calculate lambda max from the known value of mass and moment of inertia, or otherwise from the value of lambda max, which is obtained from experimentally using that lambda max you can calculate rotational constant also. Yeah, let me show you, but this is actually an approximate one. This is not a very accurate one, because here we are going to assume that the electrons are independent particles. Okay, so I'm going to make an assumption. It's a very important assumption. The assumption is that particles, that is electrons, very specifically pi electrons. Okay, here particles means pi electrons. Particles are independent. Independent means there is no interaction between particles. Okay, one particle does not know the presence of other particles. That's the meaning. Okay, and here this particular model, okay, that is particle on a ring model. This model is very specifically applicable to cyclic conjugated planar system containing even number of carbon atoms. Why? I'll tell you. Okay, say for example, I'll take benzene, C6H6, benzene molecule. Okay, for benzene, how to calculate lambda max value? By using this particle on a ring model, right? Yeah, we know that assuming the benzene as a cyclic system, so you know very well, you can in Frost cycle you might have learnt about this under aromaticity. You can construct, or you can keep the conjugated molecules in Frost cycle like this. Okay, in cyclic conjugated molecules like this. Okay, so you can take benzene and you can keep benzene like this, right? And you have alternate double bonds, and the double bond consists of pi electrons, and these pi electrons move freely throughout the molecule. Okay, and here in this model, okay, assume that the electron is moving only on the circumference of this circle. Okay, I'm just approximating this planar hexagonal planar ring as a circular ring. Okay, and I'm also assuming that the pi electrons are freely moving right along this circumference. Okay, so benzene is assumed to be a cyclic system, and electrons are moving freely on the circumference of the circle, Okay, now the question arises, what is the radius of this circle? Okay, what is the radius? To find the radius, okay, what we can do is, listen, this is also radius, right, r, and now if you see this triangle is an equilateral triangle. Okay, in equilateral triangle, okay, all the side lengths are same. So this is nothing but carbon-carbon bond length. Okay, so radius here is nothing but equal to carbon-carbon bond length in benzene molecule, carbon-carbon bond length, which is equal to 1.40 angstrom units. Okay, 1.40 angstrom units. So this carbon-carbon bond length we know. So now the radius of the circle is this 1.40. If you know radius, you can calculate moment of inertia. I is equal to mass of the electron into r square. Okay, you know I is equal to m into r square. Here the particle mass is electron mass. So electron mass into square of this radius will give you moment of inertia. So you can calculate moment of inertia. From the moment of inertia, we can calculate the rotational constant. What is rotational constant? Yeah, rotational constant B is equal to h bar square by 2I. Correct? This is the rotational constant. Okay, so from the value of moment of inertia, you can evaluate rotational constant of the molecule. Okay, yeah. Now, what I'm going to do, I'm going to fill the electrons in these assuming the benzene as a electron and ring model, okay, particle on a ring model. So this is the lowest energy level. You know very well, for this ml value is 0. Then the next level is W degenerate, which has two quantum states, +1 and -1. ml value +1, ml value -1, and for this level energy is 0. For this level energy is B. I am giving energy in rotational constant values. Okay, so here energy increases in this order. Okay, then next level has energy. This is +2, this is -2. Next level has energy 4B. In the last lecture, I have given all this information. The next level has energy 9B. Like that it goes. Okay, now I am going to fill the electrons. See, I am assuming the electrons are independent. Okay, so there is no interaction between electrons. So that is one of the disadvantage of this method. Okay, because it is just a model, that's all. Okay, using this model, we are going to make a rough estimate on lambda max value. Okay, so for benzene has 6 pi electrons. So there are 6 pi electrons, and all these 6 pi electrons are freely moving. If it is so, what is the ground energy of the molecule? Okay, lowest possible energy of the molecule, right? Pi electronic energy. So let me put 2 electron here, and 2 electron here, and 2 electron here. I am applying the Hund's rule and Pauli exclusion principle. Okay, so we have arranged the electrons based on Hund's rule and Pauli exclusion principle, and this is the arrangement which gives the lowest possible energy, pi electronic energy, to the molecule. So the lowest or the ground. Okay, let me put pi electronic energy for the ground state. Pi electronic energy, let me put ground state here, GR. That GR represent ground state. So pi electronic energy of the ground state for benzene is, for these 2 electrons the energy is 0. For these 4 electrons the energy is B, therefore 4 into B, so the total energy is 4B. Okay, total energy of the benzene molecule in the ground state. Okay, this configuration is called ground state configuration. In this configuration, the total energy is found to be 4B. Okay, listen, we cannot experimentally we cannot estimate the energy of each of these levels. That is not possible, but we can estimate the energy difference. Actually, this is the HOMO level, highest occupied molecular orbital levels, okay, and this is the lowest unoccupied molecular orbitals, right? These are all actually called molecular orbitals in the case of benzene, right? Assuming the electrons moving on benzene ring as particle on a ring. So if you assume like that, then these states represent molecular orbitals. Okay, and you know very well each molecular orbital can accommodate maximum of 2 electrons. So I put 2 here, 2 here, 2 here. Okay, now this gap can be measured. This gap is delta E. This delta E can be measured by using UV visible spectroscopy. So if you pause radiation of radiation having a particular frequency nu, then the electrons present in the lower level will absorb and goes to the excited state. Okay, so for this HOMO to LUMO transition, right, what frequency of radiation is absorbed or what frequency is required, that you can calculate by knowing the value of delta E. Okay, see what is delta E here? Delta E is nothing but energy of the LUMO level minus energy of the HOMO level. Okay, so this gap, for this the energy is 4B, for the LUMO level energy is 4B, for the HOMO level energy is B, so 4B minus B will give me 3B. So 3B is the energy gap, and you know very well exactly this energy delta E, okay, equivalent amount of this energy is absorbed in the form of photon. Okay, so photon energy should exactly matches with this delta E. Okay, now you know very well H into frequency is nothing but C by lambda, right? Frequency is nothing but C by lambda, and what is delta E? Delta E is equal to 3B here, or I can also write lambda equal to HC by 3B. Okay, this is actually lambda max. So if you know the value of see H and C are constant, if you know the rotational constant for the particle, okay, on a ring system. So here the particles are electron and the ring is the benzene ring. If you know the radius of the ring and if you know the mass of the electron, right, mass of the electron is already known. Okay, substitute that value here, you will get the rotational constant. By knowing the rotational constant, you can estimate the lambda max, that is the energy required for the transition of electron from HOMO to LUMO in benzene. You can calculate using this formula. So this is applicable for benzene molecule. In a similar manner, you can calculate, okay, lambda max values for other systems, other cyclic conjugated system containing even number of carbon atom, provided the molecule should be planar. Okay, and remember this is a rough estimation. It is not accurate one because we are making a lot of assumptions here. First of all, the molecule is not cyclic. Okay, the molecule is hexagonal molecule. We are assuming the molecule is cyclic molecule. Okay, that is the first assumption. Second assumption, we are not considering the electron-electron repulsions here. We are assuming the particles are independent. Okay, so based on those assumptions, we have calculated this lambda value. So it is a rough estimate. Okay, alternatively, you can estimate, you can find lambda max through experiment. Experimentally, you measure lambda max, substitute that value here, you can calculate the value of B, rotational constant. Okay, alternately, you can do like this also. So by knowing B, you can calculate lambda max, or by knowing lambda max experimentally, you can calculate B value. From the B value, you can find what is the bond length, right, of the benzene molecule. Okay, yeah. So this is the application of a particle on a ring system. Right, I stop here. We'll start the particle on a sphere model from the next lecture onwards. Thank you.